All right, the last section we have here is 17.1, Green's Theorem. Green's theorem is a generalization of the fundamental theorem of calculus that you learn in Calc 1, and Green's theorem is one such theorem of a trio of theorems that we will talk about after exam 3. We have Green's, Stokes, and divergence theorems. These are all extremely important theorems in vector calculus, and they unify seemingly different notions altogether. And in fact, those three theorems are just specific instances of a more general theorem called the generalized Stokes theorem, which maybe we'll talk about. Okay, so Green's theorem says that if you have a domain D, and the boundary of this domain is some simple closed curve. So what does simple mean? Simple means the curve doesn't intersect itself. Is that really a big problem? No, it's not a big problem, because really what this means is you have like two regions. You've got this region, we can call this D1, and then that little loop we had over here, that would be D2, which is fine, but that just means really you would have to apply Green's theorem once to each little section. So this is just saying, let's look at if you have one scenario here. So a simple closed curve, so some curve that does not intersect itself. It can do some pretty wacky things, but it doesn't intersect itself. It's a closed curve, meaning that it actually encloses an area. So this right here would not be a closed curve because there is no inside or outside. Everything can be filled in. There's no distinction. It doesn't isolate or section off a region of the plane. So we want something that's closed, something that does create two different regions, like an outside region and an inside region. We want this curve to be oriented counterclockwise. So I got a document that I'll post that goes into a lot of detail about why we are choosing counterclockwise. Very briefly, ultimately, whether or not we choose clockwise or counterclockwise doesn't have any long-ranging repercussions. There's nothing inherently wrong about clockwise, but simply when you write down this theorem right here, if you orient your curve counterclockwise, then this order of subtraction is this order right here. But if we were to make this just clockwise, so we strike out the word counter and we just do clockwise, then this order is reversed. So essentially, how you choose to write down this theorem depends upon your orientation. So we just talk about counterclockwise. So when you have your basic setup here, which is one region, a simple closed curve, Green's theorem, we always default to counterclockwise orientation. Okay, we will learn later, what if our region actually has like a hole in it, something like that, so that this is the interior of the region, and then we have this other curve here. How would we orient this curve? Well, it just so happens that we'd actually orient this curve this way in this case, which is not counterclockwise. So this theorem here, really the way it's set up and the assumptions that are written here, it's really only applying to your basic kind of boring domain, which is just some amorphous blob, a simple closed curve, in which case counterclockwise. So we've got a simple closed curve, and we're going to orient it counterclockwise. So if we call this domain D, then the boundary of D, the actual curve, that's denoted with this partial symbol, even though this is the symbol's used for partial derivatives. In this case, it's not meaning a derivative. There's a finite number of symbols, a finite number of things that we can write down in math. So we sometimes use the same symbol in different places. So this just means the boundary of D. So it's actually that oriented curve. So Green's theorem tells us that if you do a line integral, so there's some vector field in the background here, right? I haven't drawn the vector field yet, but there's some vector field, okay? And if we do the line integral around that boundary curve, del D, then the result of it is exactly the same thing as this strange looking, the double integral of this strange looking quantity. So this quantity does look strange, and it does kind of look mysterious, but you may recognize it because it does show up with conservative vector fields, right? This is what we check to see if, for conservative vector fields, we check to see if this is equal to this. And you could just subtract this and check to see if this difference is equal to 0. That would be the exact same thing. These two are equal if and only if their difference is 0. So that does show up. But it's important to note here, although that shows up, and we did a lot of practice with it just recently in the section 16.3 on conservative vector fields, there is nothing in Green's theorem that says that we're working with a conservative vector field. Nothing at all. So Green's theorem sometimes gets misgrouped in with conservative vector fields, thinking that it's a result that only pertains to conservative vector fields, and that's not true. Green's theorem works when you have these assumptions satisfied. So you have some domain D whose boundary is a simple closed curve and it's oriented counterclockwise. So notice that there's no additional assumptions on the vector field F. So what is important to note here is that this integral right here, this is written in the alternate notation. So we could also write this in red here. This is the same thing as the line integral over the boundary of D, f dot dr, where the vector field F has components F1 and F2. So at this point, you should have seen both notations and how you can rewrite one into the other, much like you can write this vector here as f1 I hat plus f2 j hat. Sort of the same idea. Okay, so with that being said, I do want to mention that in a document that I'll post, or should be posted already, I'll do a video over it as well. I do go into a lot of detail on where this comes from and what it represents. Effectively, I will say that this right here is the counterclockwise rotation rate. So it's the rate, I always write rotation in a weird way. I think I wrote it right the first time. It's the rotation rate. It's the counterclockwise rotation rate. In my video and the document I post, I justify this. But for now, that's why the subtraction sign changes if we were to orient things clockwise, because what's the opposite of clockwise? Counterclockwise. So if we swap to the opposite orientation, then we get a minus sign here, and that flips the order of subtraction. So, all right. What I would like to do in this video, though, is compare it to the other fundamental theorems that we know. So let's start with Calc 1. So in Calc 1, I just realized it's right in the middle of the screen. Let's go ahead. So in Calc 1, sorry about that. In Calc 1, we've got the fundamental theorem of calculus, which is the following. If you integrate the derivative of a function over some interval I, so let's say here that our interval I, let's let I equal the interval a to b. That's what we're used to in Calc 1. Well, what is the boundary of an interval? Well, in Calc 1, this is just a portion of the real number line, right? The real number line goes on forever. But if we're only going between A and B, then the boundary of this interval is simply this x value A and this x value B. So the boundary of I, this interval, is simply the 2 points, A and B. So, for the fundamental theorem of calculus, we know that this is equal to, well, let's write it in the more familiar way first. For the more familiar way, we write this as A to B, and then this would end up being F from A to B. Okay, that's what we're used to in Calc 1. But we could also write it in a slightly different way, and that is more in a Calc 3 kind of look and feel. We could put the domain of integration on the bottom of the integral, much like we have the double integral over D or the triple integral over W. We can just go ahead and put that on the bottom. And then we'd still have our derivative d dx of f dx. And then this, we could write this as over the boundary of I, because A and B, they simply are the boundary. So there's the fundamental theorem of calculus. All right. And it might not seem like this interval has an orientation, because we don't really talk a ton about orientation in Calc 1, but there is an orientation. And it's, in this case, it's specified by the positive direction of x. So in a more abstract setting in calculus, dx actually represents a, let's just say, sort of like, we know how I hat represents your cardinal direction for vectors, right? You can specify how to move along in the horizontal direction by multiplying by different weights, different scalar multiples of I hat will push us different directions, different amounts in the x direction. Negative values take us to the left. Large positive values take us more to the right. Well, we call that I hat a basis vector, but we can think of it as like our cardinal direction, how we specify directions to somebody. Well, in 2 dimensions, we'd use I hat and j hat, or east and north, because negative east is just west, and negative north is just south. So we really only need those 2 directions because their opposites give the other 2. Well, the same thing kind of happens when you have a single variable. These differentials actually tell you vector field directions. So in this case, dx actually is telling us, dx is really specifying this vector. That's what dx is kind of specifying. So in this case, the orientation is actually this way. So because of that, we do final and initial. If we had a negative here, right? If we put a negative in front here, well, really, this is -1 times this whole thing. So we could put the -1 anywhere. We could make this times negative f. We can make this the negative derivative, or we could make this times negative dx. In which case, this would reverse the direction of that basis vector, which would mean we could be going this way. And that's exactly why, if you have a negative in front, you're allowed to just switch this order here. You're really reversing the orientation. I don't know how many instructors use the term orientation in a Calc 1 setting for that. But that's exactly that little fact that you were told in Calc 1. The fact that negative the integral from a to b is informally the integral from b to a. So that's fundamental theorem from Calc 1. Okay, Green's theorem. I'm going to go ahead and start with the double integral on the left-hand side, unlike the previous page. So the double integral over some domain D, we've got this expression here, dA. This is equal to the integral over the boundary of D, f dot dr, or remember, this is identical to the line integral over the boundary of D, f1 dx plus f2 dy. So with Green's theorem here, this expression here that I justified to you, this represents a counterclockwise rotation rate. Well, it's a rotation rate. It's a rate of change. It's not a rate of change of position. I mean, it kind of is, right? Because if you're rotating, you're changing position, in a sense. I mean, you could be still and rotating, in which case you're not changing position, but you are changing your perspective. So this is a rate of change. It's a rate of change of rotation. But remember, what's a rate of change? A rate of change is a derivative. So over here we have the rate of change of the value of f, which f, we can think of this as a position, if we want to. This is a rate of change of rotation, how you are curling or how you are rotating. So both this expression here and this expression here, both are derivatives. And maybe I put that in quotations because I know that this box down here does not really, when you look at this, you see partial derivatives, but you might not think of this in itself as a type of derivative. So this is a special type of derivative. In the next theorem that we'll learn after exam 3, Stokes theorem, this Stokes is really just a more general version of Green's. Green's theorem, you're restricted to looking at things in the plane, where Stokes, we're going to look at this on like the surface of things. So we can actually look at surface integrals and things like that. And in Green's theorem, you end up seeing this looks like this. It's the curl of f. And in this case, it is very clear that there's a derivative here because we did talk about how the curl is a type of derivative. So right here, it's a little bit, I think, obscured because of the dimensionality, but this is a type of derivative. So because of that, both the fundamental theorem of calculus that you learned in Calc 1 and Green's theorem, they both start off with the derivative of a function. This is a type of derivative of what function? Well, this vector field. It's a type of derivative of this vector field. So we have a derivative of a function in both cases, because a vector field is a function. It's a vector valued function, but a function nevertheless. So we have the derivative of the function. We are integrating over some domain. Sure, this is a single integral, and this is a double integral. But the reason why this is a single integral is because this function has one variable. This vector field has two variables. It's a two-dimensional vector field, so there's two integral symbols here. But in either way, we are integrating over some domain. This is a one-dimensional domain. This is a two-dimensional domain. Then what you end up having is the theorem states that this converts into, well, we had one integral over here, now there's zero integrals on this side. We had two integrals here, now there's one integral. So each of these reduced the number of integrals by one. So we subtracted one integral off, we peeled one off, and then we integrate on the boundary, or sorry, not integrate, we evaluate, I should say. We evaluate the function without the derivative, right? Over here we had a derivative, And we came over here, we got rid of one of the integrals, we got rid of the derivative, and then we're able to evaluate this just along the boundary. Well, the same thing happens here. We had a derivative of a function. We peeled off one of the two integrals. We went from the domain to the boundary. And when we actually, and we evaluate this along the boundary. So to me, these two things are really the same kind of process. You start with a certain number of integrals, who knows? Over some crazy domain, you have some type of derivative of a function of some kind, and then you'll peel off one of those integrals and go over the boundary of that thing. Don't worry, we're not going to be doing 5 integrals or 4 integrals here. But this idea of taking a certain number of integrals of an appropriate type of derivative over some domain, that there's this idea that can be evaluated by looking at no derivative of that function, that object, one less integral, and we're only going to do this around the boundary. Okay, so that's Green's theorem, and next video we'll actually start and see how this works.